So, welcome to the new lecture again for dielectric materials, fundamentals and applications of dielectric ceramics. So, let us just briefly recap the last lecture. So, in the last lecture we basically talked about the frequency dependent variation of dielectric constant at low frequencies. Okay. So, we looked at essentially how the dielectric constant varies at lower frequencies. So, it goes from static to, so basically we looked at epsilon Rs, epsilon R infinity, and the difference between the two is the one that you observe at the lower frequencies. And then we also looked at the variation of tan delta. So, this is low. So, this dipolar contribution is not resonance type of contribution, rather it is a relaxation kind of behavior. So, that is what we looked at. And then there is also a temperature dependence as a result, since it is a relaxation kind of phenomena, it is more like diffusive Arrhenius kind of behavior. There is a Arrhenius kind of relationship though. So, as the temperature changes, the change in the tan delta peak, it shifts to higher frequencies as your temperature changes. So, this is tan delta, this is omega, and the peak will shift to, so right as your temperature increases. So, basically it requires lesser time for dipoles to respond, and dipoles become weaker as you increase the temperature. And then we looked at the phenomena of impedance spectroscopy, because to analyze the dielectric materials it is often useful to model it in a circuit form. So, we looked at one circuit, for example the Debye circuit, through which you represent a dielectric as a resistor and a capacitor in series, and then you have so this is R2 C2, and then you have C1, this sorry I mean you can say R1, and that's entirely up to you. Okay, let me just draw it little. So, this is okay, yeah. So, this is okay. For what I did was, it was R1 C1 and C2, okay. But it does not matter, I mean R1 C1 and C2 are entirely dependent upon your choice. But what basically it means is that you will have, for a perfect dielectric, when you plot epsilon R double prime as a function of epsilon R prime, you should obtain a perfect semicircle, okay. It does not look like a perfect semicircle, maybe something like this, okay. So, this is perfect semi circle, right. And as we saw that the peak of this is at omega tau is equal to 1, and from this you can determine various characteristics. So, we looked at, for instance, so this was actually R2 C2 C1 in the context of this. So, essentially what we will have is, so the frequency is increasing in this direction. So, this contribution is your low frequency contribution, and this is your high frequency contribution. So, this is basically your epsilon R infinity, and this will be epsilon Rs minus epsilon R infinity, okay. So, sorry, epsilon Rs, just one second, let me see. So, yeah, so this will be epsilon Rs minus epsilon R infinity. So, that is what your contributions will be. So, you basically what will happen is that if you work out C1 and C2, your C1 will be epsilon R infinity and C2 will be epsilon Rs minus epsilon R infinity divided by C naught, okay. So, if you look at the contributions here, this will be epsilon R infinity, this is basically C1 corresponding to C1, and this will be corresponding to, so this is epsilon Rs, this will correspond to C1 plus C2 basically, okay. So, this is what you should obtain, perfect semicircle, and you can draw a right angle triangle anywhere in this semicircle, and you should get a equation of semicircle. Using this, now this can also be modeled in the form of impedances, because we know that impedance is related to admittance, admittance is related to your dielectric constant. So, this can be modeled in the form of impedances as well. And we saw that when you measure impedance from an impedance analyzer, basically you are measuring Z theta. Okay. So, real part of impedance will be Z mod Z cos theta, and then you will have mod Z sin theta. Okay. So, you can determine what are the real parts of impedances, what are the imaginary parts of impedances, and they will allow you to and we know that impedance is nothing but Z star is equal to Z prime minus I Z double prime, and Z prime can be modeled as R divided by 1 plus omega R C square, which is nothing but omega square tau square, and Z double prime can be omega R square C divided by 1 plus omega R C square, which is nothing but omega R into tau divided by 1 plus omega square tau square. So, essentially it is nothing but R into omega tau plus 1 over omega square tau square. And so, this is basically the variation of, so you can see that there is a frequency dependence of impedance on the, so frequency we saw earlier. So, this impedances can be worked out as we know that Y was the admittance, admittance was worked out as tau square omega square tau 2 C2 divided by 1 plus omega square tau 2 square plus I omega into C1 plus C2 divided by 1 plus omega square tau 2 square. This is what we worked out earlier, okay, and this is nothing but 1 over Z, and we, so this is essentially from this Z one can work out what is modulus as well. Modulus is given as, this is electric modulus, the electric modulus is nothing but M star is nothing but J or I omega C naught into Z star, okay. So, basically it becomes M prime minus I M double prime. The advantage of using this modulus and impedance spectroscopy together is that modulus tend to amplify the contributions of higher frequency, lower frequency contributions, but since you can see that I is M star is nothing but I omega Z star C naught Z star, this tends to amplify the contributions at the higher frequency. So, often you will see the semicircles at higher frequency are subdued in the impedance spectroscopy, but when you do modulus spectroscopy, the contributions of high frequency contributions, they are more clearly visible in case of modulus. So, they are complementary to each other in the sense that they are not derived from something differently, they are all dependent upon each other, but it is just that a different way of representing the two properties. And also if you now if I make a table of the complex relationships. So, let us say we make, so if you like, because we know that these are related to properties such as impedances, admittances, which are complex properties. So, complex properties relationship chart can be made, which helps you in analyzing dielectric materials little better. So, let us say on this axis we plot, so here we have Z star, here we have Y star, and we have C star, and we have M star, right. And Z again we say Z star, Y star, C star and M star. So, Z star is nothing but Z star, this becomes 1 over Y star, and this is nothing but 1 over I omega C star, and this becomes M star divided by I omega C naught. So, Z star is equal to 1 over Y star, it is equal to 1 over I omega C star, which is the complex capacitance, and this is M star divided by I omega C naught, okay. So, now, so and all of these properties are, so let me just also write how these properties are written as. So, as I said earlier, sorry, Z star will be equal to I z prime plus I z double prime. So, when you write z prime is z star is equal to z prime plus I z double prime. On the other hand, m star can also be written as m prime minus I m double prime, and then we have C star is basically C prime minus I C double prime, which is the complex capacitance, and admittance is given as y star is equal to y prime plus I y double prime, and dielectric constant as we know is epsilon r star is equal to epsilon prime minus I epsilon double prime. So, this is how these properties are written. So, and when you write this in the table form, so z star will be equal to z star will be equal to 1 over y star, it is equal to 1 over I omega c star, it will be equal to m star divided by I omega c naught. Similarly, if you write y star, it will be 1 over z star, this will be equal to nothing but y star, this will be I omega c star, and this will be I omega c naught divided by m star. Now, if you write for C star, it will be 1 over I omega z star, this will be y star divided by I omega, and this will be C star same as that, and this will be C naught divided by m star. And when you write for m star, this will be m star, this will be I omega C naught z star, this will be I omega C naught divided by y star, and this will be C naught divided by C star. Okay. And if you are wondering what C naught is nothing but epsilon naught A over D, right. This is the vacuum capacitance. So, this is how these complex properties are related to each other. Generally, we use Z and M for determination of various components. So, what might happen, for example, is you may have a spectra like this, you may have spectra which is like this. So, this is let us say Z double prime, this is Z prime. So, basically we have two semicircles here, one is for low frequency and one is for high frequency. Both of them have tau 1 and tau 2. So, as a result, what will happen is that the time constant for this semicircle belongs to one entity. So, generally low frequency contributions in solids will come from grain boundaries, whereas the high frequency contributions will come from grains. So, when you plot, let us say, temperature dependence of these plots. So, how does the temperature dependence vary? So, for example, if you want to plot Z prime as a function of frequency, so Z prime as a function of frequency might vary something like this. As you increase the temperature, the curve will shift to right. So, as you increase the temperature, the curve will shift to right. So, temperature increases. Similarly, the peak in the Z double prime will show correspondingly, if you plot Z double prime, they will show corresponding peaks. These peaks will also shift towards right, and these peaks correspond to basically omega tau is equal to 1. So, what you do is that when you plot 1 over t, and we know that tau is equal to tau naught into exponential of minus qa divided by kt. So, when you plot ln tau, we get slopes like these, for example. So, you will get two distinct regions in which you will have one slope and another slope. So, this is for example at low temperature and this is at high temperature. So, there is one entity which has certain activation energy at lower frequency, there is certain activation at higher frequency. So, it might happen that you will have, so this is for example it could be grain boundary region, this could be grain region. Okay. So, these and they also have different frequency dependence, because the grain for example this particular region on the right, this may respond at higher frequencies, whereas the region that you see on the left, which is for grain boundaries, it may respond at lower frequencies. So, that the different type of peaks show different behavior in the evolution of Z and M. So, basically for complete analysis, you need to look at Z versus Z prime versus F, Z double prime versus F, M prime versus F, M double prime versus F. From these you can determine R and C, the resistances and capacitances separately, because most of these entities have. So, ideal Debye capacitor looks like this. This is your ideal Debye material, but in reality your material may look like, in reality your material may be modeled like this. And so on and so forth. So, this is one RC circuit, this is another RC circuit, RC1, RC2, this could be for grain, this could be for grain boundary, and then you have series resistance, which is, let us say, contact resistance RC, and so on and so forth. So, reality may give you different resistances and capacitances. So, when you need, there is and this happens especially in polycrystalline material or materials with lot of defects, where resistances and capacitances vary dramatically. As a result, you need to separate out the resistive contribution and the capacitive contribution. So, for example, when you see the electric constant variation as a function of frequency, ideally it should be like this, but in most cases you will obtain a behavior which is like this. This decrease of the electric constant suggests as a function of frequency that you have extrinsic contributions. So, which could be defects, for example, which could be vacancies in the system, variety of defects. So, from this, from the blue plot, it is easy to measure what the dielectric constant is, because dielectric constant is, there is a contribution which is frequency independent, but here you have a frequency dependence. So, how do you separate out the real dielectric constant? What is dielectric constant is difficult to tell. So, that is why you need to carry out impedance analysis, measure Z and theta. From Z and theta you work out what is Z prime, Z double prime, then you work out what is M prime, M double prime, then you work out what is different R's, R1, R2, etc., different C1, C2, etc. Then looking at the values of R1 and C2, you have to make a judgment. So, generally you will find, how do you make a judgment then? So, for example, if you look at, if you work out a specific capacitance is given in farad per meter, okay. So, or farad per centimeter, let us say in this case. So, generally if the capacitance is of the order of 10 to the minus 12, it is because of bulk. If it is a grain boundary, then it would be of the order of minus 11 to minus 8. So, this would be grain boundary. If it is a surface layer, it would be minus 9 to minus 7 for surface layer. And let us say if you have electrochemical reaction, it may be of the order of minus 4 for electrochemical reaction. So, these values of capacitances will give you an idea about which entity are you talking about, whether you are talking about bulk or whether you are talking of grain boundaries. So, it is very important to know about what you are doing. So, I will give you certain references that you may go through for impedance spectroscopy. For example, there is a nice paper written by, so there is a group in Sheffield University which has worked extensively on this. So, let me give you the reference. So, this, if you look at, so reference for so you can read this paper by, so this paper advanced, it is in Advanced Materials Journal, volume 2, 1990, page 132. This is by authors called as Irvine, Sinclair and A.R. West. It's a good paper that gives you some idea about the impedance spectroscopy. Then impedance spectroscopy, there is a book, Impedance Spectroscopy, by Ross MacDonald. It's a vast topic, impedance spectroscopy. I cannot talk about this in this course, but I just wanted to tell you what you can do. The things that you can do is that you can basically look at the microscopic mechanisms behind its capacitances and find out any resistances in and separate out the resistive and capacitive contributions, work out the true value of dielectric constant, which is purely from the capacitive contributions, not from anything else, by properly modeling the impedance data using these kind of circuits, and this is helped by doing this impedance and modulus spectroscopy, and the measurement is basically measurement of impedance and angle Z and theta, which is done on a impedance analyzer. So we will now stop this part of impedance spectroscopy, and we will briefly now look at finishing this part of linear dielectrics is dielectric breakdown. Okay. And this dielectric breakdown is basically about failure of dielectrics. Okay. So dielectrics work under a certain electric field. When basically they stop becoming dielectrics, that is when dielectric breakdown occurs, and generally it is denoted in the form of large increase in current or conductivity of dielectric. So this is what basically dielectric breakdown means. So essentially, if you plot current density as a function of field, so for very large field the current density will remain low, and suddenly at some point the current density will shoot up. So this is where you will have breakdown, and this field is denoted as EB, which is the breakdown field. So essentially this is what we mean by dielectric breakdown. So in many cases the breakdown may not be sudden, it may be gradual, whereas in some cases it may be very rapid. So if you look at the breakdown, the strength of certain materials, so the most important material, something that we come across regularly is air. When you see sparking in the air, right? So sparking is basically ionization of air. Air has a breakdown field of 3 megavolt per meter, which is about 30 kilovolts per centimeter. Okay. And now if you compare certain materials, so let us say we have materials and then we have EB, and we compare this with the so this is in kV per centimeter. So if you look for glass has a value of 200 to 400. Okay. If you look at mica has a value of about 200 to 700. Look at polymers, they have a value ranging from 50 to 900. If you look at Al2O3 ceramic, it has a value from 200 to 300. If you look at barium titanate, it has a value of roughly 300 for single crystals. And silicon carbide, that is silicon oxide, that is used in ICs, it has more than 10,000 kilovolt per centimeter. So you can see that for most materials the value of breakdown field is significantly larger than the value of breakdown field for air. So if you now compare, so for example on electric pole sometimes you see the sparking, and that is mostly because of failure of the capacitor that you have, and the field in the capacitor becomes so high that the air molecules in the vicinity, they get ionized. Also materials contain pores, within the pores you have entrapped air, and when the field is applied, this air gets ionized and sort of it leads to blasting of the material or failure of the material. So there are various mechanisms because of which this failure occurs. So, the breakdown mechanisms are basically so the first one is intrinsic breakdown. Intrinsic breakdown is basically based on lattice ionization, and what it means is that there is a substantial increase in the electron temperature. Okay. And this is basically a field dependent mechanism. When you apply very high field, the electron temperature rises. As a result, the material it becomes very conducting. So, field dependent, large increases in conductivity beyond a critical field. Okay. Then we have another mechanism which is called as thermal breakdown. Thermal breakdown is basically because of heat dissipation. So, materials have defects and various other reasons which lead to increase in the temperature of the material. This is basically true for many of the bulk materials which contain defects, and they have intrinsic heating, and this generally happens at temperatures which is greater than room temperature up to about 300-400 degrees centigrade, something like that. And basically it can also be, the process can be gradual, it can happen at various time scales, and it may also be dependent upon the sample geometry. So, so this is thermal breakdown, and then we have avalanche breakdown. So, essentially this is because of heat dissipation or heat buildup. Okay. And then we have, and this is basically because of sudden increase in kinetic energy of electrons leading to large. So, any processes, kinetic processes which lead to multiplication in the electron density and electron velocities, they lead to large increase in the conductivity. So, sudden avalanche means there is a deluge of electrons, and that leads to a large conductivity. So, this is another one, and this generally happens in thin films. Okay. And then you can have other breakdowns, such as you can have dielectric discharge. And dielectric discharge could be because of, for example, porosity. If you have sort of porosity or air entrapped in the air, then discharge is created inside the material. When you apply field, the air gets ionized, and which is basically electrical discharge, and sort of leads to material ripping apart. And then you can also have electrochemical breakdown, which could be because of transport of materials from one place to another within the same material. So, some species may transport to another position, and another species may transport to another position, which leads to changes in the chemistry inside, or ionic defect chemistry, leading to change in the conductivity. So, if you want to read more about breakdowns, I can refer you to this book, Principles of Electronic Ceramics by Hench and West. So, this is sort of a short introduction to linear dielectric materials that I have given to you. basically covering from fundamentals of dielectric materials, the dielectric polarization, dielectric constant, mechanisms of polarization, what kind of polarizabilities that we have. We did some analytical treatment of dielectric polarizabilities of ionic, electronic and dipolar, looking at the macroscopic as well as the microscopic scale in terms of frequency dependence. And finally, we talked about Debye equations and impedance spectroscopy, how to use impedance spectroscopy to characterize these materials, and finally about the dielectric breakdown. So, hopefully this has given you a good idea about linear dielectrics, how do you work with them, how do you characterize them, and in the next class we will start our discussion on nonlinear dielectric materials, which basically we will talk about some basics of piezoelectric, ferroelectric and pyroelectric materials, what distinguishes them, and individual physics and application of these materials. Okay. Thank you very much.